So our goal here is to apply Euler's method for systems. There's our system. It happens to be a linear system, but Euler's method applies to nonlinear systems too. In this case, with delta t to be 0.5, I can pick any positive number that I want there. Based on these initial conditions, x0 equals 1 and y0 equals 1, that does correspond to an initial condition vector. You could write as y0 equals 1, 1. It is helpful if you think of Euler's method in the way that I tend to, as a vector instead of a system of scalar equations, to specify what the vector field is for this system. The right-hand side, it can be thought of as a vector field. That's what I've essentially got there. You can think of that as a function of the vector y, or you can specify what its components are, little x and little y. And that's what you can go into the Euler's method equations. When I wrote it on the board here, I did include a t here. I included the non-autonomous case, but this example is autonomous, so I didn't bother. I actually forgot to include the t here, but it is an autonomous system, so we don't need a t down here. Okay, but in Mathematica, which we'll use to confirm our answers here and visualize it, it is programmed in such a way that you could deal with a non-autonomous system as well. Anyway, so let's go ahead and apply it here. You can make tables like you found in the book, or I prefer writing things out in vector form. Again, y0 is what's given. Y sub 0, y0 is the given vector 1, 1. That's easy. T0, the initial value of t, is 0. I think it is good to emphasize what t is each time. T1, the next value of t is going to be, using the first recursive equation up here, is going to be t0 plus delta t. So that'll be 0 plus 0.5 is 0.5. And y1, this is one step of Euler's method here, is found from this equation. So it's going to be y0 plus delta t times f of y0. What's going on here? We'll draw a picture after we plug in the numbers. Y0 is 1, 1. Delta t is 0.5. What's f of y0? Well, it's f of 1, 1, whatever that happens to be. What do I need to do to figure out f of 1, 1? I need to go up to the formula for the vector field. Plug in little x equals 1, little y equals 1. I'll get -4, -4, it looks like. -4, -4. So this becomes 1, 1 plus multiply the scalar through the vector. In both spots, you'll get -2, -2. Add those vectors, you'll get -1, -1. I'm sure this is not very accurate. This delta t being 0.5 is too big to be very accurate here. We're just illustrating the method is all we're doing. What's going on geometrically in the phase plane at the point 1, 1? The vector field has components -4, -4. The actual vector in the vector field is kind of a long vector like that, with components -4, -4. The direction field, you would shorten this vector to indicate you're heading off in this direction, but the length of the vector is the speed of the solution curve at that moment in time. It's not going to go through the origin. This is resulting in an inaccurate estimate. We know for this linear system we saw last time that it's got an equilibrium point at the origin. It can't touch that. It can't pass through that. So this is very inaccurate. But we are essentially multiplying this vector by 1/2, scaling it down by a factor of 1/2, and adding that vector to the original vector to get this new one. This is not a good initial condition to pick for this example. Another strange thing happens in the second step. When we use Mathematica, we use a different value of delta t. For the second step, t2 is t1 plus delta t. 0.5 plus 0.5 is 1. Time has gone up to 1. What's the next value of y? I think we head back through the origin here, actually, to the symmetric point, I think is what happens here, but that is a rare thing. Now we're at the point -1, -1. Delta t is still 0.5. What's f of -1, -1? I have to plug in little x equals -1, little y equals -1 back into the vector field. And I get positive 4, 4. Yeah. We're just going to keep bouncing back and forth with this example, with this value of delta t. If I pick a smaller value delta t, it'll be better, and it won't do this necessarily. We're back to 1, 1. Okay, that doesn't typically happen. Let's go ahead and implement this on Mathematica now. And let's use a smaller value of delta t on Mathematica to hopefully avoid this situation. So I copied and pasted the code from the solution key to the optional problems. That's going to work more generally when my right-hand side functions might also be dependent on t for a non-autonomous system. Our system is autonomous. We don't really need the t in there, but I'll leave it there anyway. It doesn't hurt. The right-hand side, the first component of the vector field is -2x minus 2y. The second component of the vector field is -x minus 3y. So those become the little f and the little g. We want to implement Euler's method in Mathematica with nest list, because nest list is the most efficient way to iterate functions. Use recursive equations like this. And this code does it in general for a general little f and a general little g. This is defining a new function that I'm calling capital phi here. Maybe that's an unfortunate choice. This is not a flow. It's not a solution. It's just a function that I named that it's going to be the function that I iterate. Probably unfortunate that I use that notation. It's not consistent with our other use of capital phi. Nest list is iterating that function for whatever value of delta t that you pick. Let's go ahead and use the 0.5 to start with and see what happens. In this list, the first coordinate is, or the first element is the initial value of t, 0. The second one is the initial value of x. The third one is the initial value of y. So I want to change those to 1, 1. EM is just the name of the list that I get out. If I don't have this table form code here, and I get rid of the semicolon, I will see a list of points out. The first coordinate keeps going up by 0.5, from 0 to 0.5 to 1 to 1.5 to 2 to 2.5, etc. And yeah, for this example, the x and y coordinates keep bouncing back and forth between 1, 1 and -1, -1. But if I pick a smaller value of delta t, it should work better. Yeah, that's working better. Now I changed delta t to being 0.1. And now I'm seeing delta t go up by 0.1 each time. And the x and y coordinates are not going back and forth. They do stay the same. That's interesting. You might wonder why that's happening. That doesn't happen in general either. But they're more well-behaved, you might say, behaving more predictably and heading towards 0. We're heading toward the origin here. It's not surprising. We know the origin is the equilibrium point. And we remember from the other day, the other solutions are going toward it when we drew the slope of the phase plane for this. Table form, all it does is it presents the data in a table, a nice table. So here are the values of t, here are the corresponding values of x, and the corresponding values of y. If I pick a different initial condition, like say 2, 1, then the coordinates will not all be the same. They aren't. Okay, this is resulting in data that's giving us coordinates that are not all the same. Let's stick with that initial condition now. This code down here is once again programmed to work more generally for possibly non-autonomous systems and possibly even non-linear systems as well. Notice this is ND solved, not D solved, and not D solved value. The capital N there is essentially getting a numerical approximation instead of an actual formula, which for nonlinear systems in general is something you have to do. It'll work for linear systems too. So I'll go ahead and keep it as is. Let's change this initial condition to 1. This is going to approximate the solution of this initial value problem, t going between 0 and 2. That's what ND solve does. You don't have to worry about how it works. I will tell you it's more accurate than Euler's method is. To actually plot these points that you see here, the x and y coordinates in the graph that we're going to see, it is required to do this. And without explaining too much, what drop does, this drop EMI, 1, essentially drops the first coordinate in the data that we got from Nestless, the t values, the 0, in this case, the 0, the 0.1, the 0.2, the 0.3, etc. We're dropping those t values. The 1 means drop the first coordinate, so to speak. Drops it. EM no time gets rid of the time values and just focuses on the x and y values. And then that list, EM no time, can be plotted with list plot, as I'm doing down here a couple ways. This joined arrow true within this list plot will join the points that I get with probably line segments. And then this is plotting the points themselves. It's not super efficient to have to do that twice, but it was a way that worked. Vector plot, as usual, plots vector fields. Stream plots the streams. Parametric plot plots the solution curve itself. And when you use ND solve, you have to do something funny there. You have to do this kind of stuff, which is very confusing as well. Don't worry about how that's working. Just copy and paste, okay? You don't have to worry about how that's working. This should produce a graph. Yeah. Showing both the true solution curve in pink, that's the true solution curve, and the approximate solution curve in green here with the data from Euler's method. And we see the vector field are the little short straight arrows scaled down. It's really a direction field instead of the true vector field. And the stream plot produces these curves that are supposed to be solution curves. And you can see this pinkish curve is seeming to follow the stream plot. And Euler's method is actually not doing too bad here. This is well behaved enough that the green curve from Euler's method pretty closely matches the pink curve that's closer to the true solution curve. But let me remind you that this is a linear system, and therefore we actually can get formulas for the solutions that can be found from the matrix exponential. Let me remind you the beautiful generalization. I'll show you that it works in Mathematica. And then I do want to talk about flows a little bit before we talk about linear algebra a little bit. So remember the beautiful generalization that I talked about last time. It's for linear systems. So the vector field is a linear vector field. It's a matrix times the vector y. Arbitrary initial condition, y of 0 equals y naught. It's got a unique solution because I've got a unique initial condition. I'm imagining y naught to be fixed here when I think about this at first. The solution, if I go ahead and use a capital phi now here, not the same as what I used in Mathematica, capital phi. Capital P sub y naught, emphasizing what the initial condition is, of t, is the matrix exponential e to the ta times y naught. That's the beautiful generalization. That's my terminology. Beautiful generalization. Well, it's certainly beautiful because it's a fairly simple equation here. That's why it's beautiful. And it's a generalization of the scalar case. I mentioned that last time. If these were scalar equations, if it was not a vector y, but a scalar y, and A was not a matrix, but a number, it's essentially the same answer, though we typically put the initial condition in the front. Here I want to put the initial condition to the right because this is in general an n by n matrix times an n by 1 column vector. That's our standard way of thinking about this. And the result is an n by 1 column vector. When you multiply, I can multiply the matrix times this vector, and the result is an n by 1 column vector. Let's apply this here with Mathematica to help. Again, a lot of what we're going to do in coming weeks, next month or so, is talking about how to find the matrix exponential, essentially. So now we're just relying on technology. Let me go ahead and define the matrix A. And let me go ahead and define capital Phi. It's a new capital Phi. Should I use a subscript for the initial condition? I could. Maybe as a list with the components listed. It's one way to do it, at least. It's going to be a function of t. What is it? By the beautiful generalization, it's the matrix exponential of t times A times the vector whose components are x0, y0. The star is necessary for a scalar times a matrix. A period, a dot is necessary for a matrix times a vector or a matrix times a matrix. Semicolon just suppresses output in case I've forgotten to mention that to you. I would like to see what this formula looks like in matrix form. Maybe we have to simplify it as well. Well, that's not too bad. I showed this to you last time. You could confirm this with d-solve value. I did that last time. If I pick a specific initial condition like 2, 1, it does simplify, maybe even more if I do simplify here, or expand. Expand tends to work better. There we go. And if you do a parametric plot of that parametric curve, you'll get something that looks like the green, the pink curve did. Technically, it's magenta. Let's change the plot scale. Plot range. There we go. That is the same pink curve that we saw above. It's the solution. Well, technically, that's the exact right curve. ND solve earlier was technically producing an approximation to this, but it would be so close you wouldn't be able to tell the difference. Okay, and I could go back up here to this parametric plot and replace this with what I just did, the capital Phi sub 2, 1 of t. I could do that replacement there, and we get the exact same picture. Again, with Mathematica, you really have to completely understand how things work. A lot of times you're just copying and pasting. I did briefly explain things here, but you might have forgotten already. Copy and paste and make appropriate changes. You probably forgot already, I should say. Mathematica is learned by copying and pasting other people's code or code you might find in the help browser menu and changing things and mimicking and looking to adjust things based on what you can find in the help menu. The documentation center is the official name of it. Go to the help menu, Wolfram documentation, and for example, look up. For example, if you wanted to know how ND solve work, you could look up ND solve. And it's one of the harder commands to use, actually. What you find at the top is not typically so helpful as the examples and just copying and pasting and modifying examples. But it takes a lot of working with and just experimenting. We should also emphasize the flow idea. What's the flow concept here? The flow concept essentially is to take this equation, the equation for your solution, and think about it in a new way. And to emphasize it's a new way, I use a different version of phi, fancy phi. Make t a superscript. So time becomes a superscript. And the initial condition becomes the true variable in a sense. When you think about this expression, at least at the start, think of t as fixed and think of the initial condition vector as the variable. And the formula is the same though. Why is this worth doing? We'll get to that. When you think of t as the variable, when you look at the formula in this way up here, it's the parametric curve that I just plotted with parametric plot. It's a curve. It's not a linear function. It involves exponentials raised to various powers of t. Not a linear function. When you think about it this way, and you think of t as fixed and y naught as the variable, it becomes a linear function. It becomes a linear transformation, in fact. What's the matrix? The matrix exponential is the matrix. It's that, if t is fixed, that fixed matrix times this variable vector. It becomes a linear transformation. Why is this worth doing? For a couple different reasons. One reason, one big reason that I really emphasize a lot in coming weeks is that it allows you to relate the solution of the differential equation to a solution of a difference equation, helping us tie together differential equations in linear algebra is another tie. I'm going to emphasize a lot something called the time one map, i.e. little t equals 1. Phi superscript 1 of y naught is e to the 1 times a times y naught. 1 is a scalar, a is a matrix, but when you multiply a scalar times a matrix, you multiply every entry of the matrix by the number 1 in this case. This is just e to the a times y naught. This is just one specific example of this. This really includes infinitely many functions because there's infinitely many values of t that I could pick. What's the simplest positive number to pick? How about 1? I could take this function of y naught and create a difference equation from it. Not differential equation, difference equation. Y sub n vector equals the time 1 map, not applied to y naught, the initial condition, but since this is going to be a difference equation, y sub n minus 1. In this case, that's e to the a times y sub n minus 1. That matrix times that vector. What's the solution of this difference equation? You can find it by iteration. Just like before, just like the scalar case. Yn is e to the a times yn minus 1, but yn minus 1 is e to the a times yn minus 2. Use the associative law, I guess that's the same as this. And I guess e to the a times itself, is that e to the a squared? And do properties of exponents hold here? Is this e to the 2a times yn minus 2? Yes, it is. And that pattern can continue until in the end, you get e to the n times a times y naught being the initial condition vector. And this happens to be the same as the solution to the initial value problem for the differential equation evaluated at time n. Now, this may not seem like it's necessarily very significant, but it is. We're saying if we solve this difference equation by iteration to get this, assuming all these calculations are valid, I haven't proved that, but they are, we get the same thing as the solution of the original differential equation with that initial condition evaluated at time n. This happens for linear systems for this reason. It also happens for nonlinear systems as long as they're autonomous, as long as the right-hand side doesn't depend on t. And it's for those autonomous equations that what's called the group property of the flow holds. I've mentioned this before. You got an autonomous equation, initial value problem. And you got the solution for that initial value problem written like this. And you define the flow to be the same formula, whatever the formula is. But you think of t as fixed and y naught as the variable. And when you do all this, what results is the group property of the flow. Sometimes I just call it the flow property. And that says this. When you compose phi superscript s with phi superscript t, it's the same thing as adding the s and t and evaluating phi superscript s plus t at y naught. And it definitely happens when your system's linear. When your system is linear, this is equivalent to e to the sa times e to the ta times y naught equaling e to the s plus t times a times y naught for a linear system. And it should seem reasonable that these are equal, because it should seem reasonable that e to the sa times e to the ta can be found by adding those exponents. And then you could factor out the a. Again, I haven't proved anything here. But if you trust mathematical patterns translating from scalars to vectors, this should seem reasonable that this works. And it does work, but it takes proof. The proof involves infinite series of matrices and what it means for those infinite series to converge. So it's very subtle, very advanced actually, to be able to prove this. But it should seem reasonable. It's one of these things where, again, you may be able to follow each step, but it's like putting it all together in your mind just feels kind of overwhelming. It's something you just got to continue to think about. One reason that it's important is because it ties together the differential equations and the difference equations. Another reason that's important comes later in chapter 5. The flow idea helps us think about and prove things, some very significant things in chapter 5. We'll just put it that way. And visualize things nicely as well. I actually did a recent lecture where I visualized things in kind of a fun way. The flow is like being an oil slick that spreads out. Okay. And this is all related, in case you're wondering, to fluid mechanics. But we are doing the easy case for the most part as far as our drawings. 2D, like a 2D flow of water, a thin layer of fluid. Okay, you can try to set up experiments to do such things. Mostly in fluid mechanics, you're interested in 3D flows, not 2D flows. But 2D flows are a lot easier to understand, so we mostly want to stick with those. 3D flows that are realistic, it's very hard. You heard of the Navier-Stokes equation? Nobody? Okay, if somebody's saying yes. Navier-Stokes equations are for fluid flow in 3 dimensions, and they're very complicated, and you can numerically approximate solutions, but there's a $1 million prize for showing that in certain situations, solutions even exist. It's called a millennium problem. There are like 6 millennium problems. I think one's been solved. Maybe there's 7. One's been solved, but one of them is proving the Navier-Stokes equations even have unique solutions in certain situations. And nobody's been able to do it. But if you can, you get $1 million. It's all related in some pretty advanced ways.